So the first one, write an equation in point slope form of the line perpendicular to the graph of 2y minus 6 is equal to x. All right. The point slope form of a linear function, just make sure that's off, is y equals m times x minus x sub 1 plus y sub 1. All right. So I need the slope. I have a point. They told me the point already. So the 4 goes in for x1 and the -1 goes in for y1. I just need a slope. Now, perpendicular lines have negative reciprocal slopes. So I'm going to add 6 to both sides. Get 2y is equal to x plus 6. Then I'm going to divide everything by 2. When you simplify, you get y equals 1/2 x plus 3. The slope for this equation is 1/2. All right. Now I want the negative reciprocal of that. So I'm going to put in a -2 here for the m value. All right. So we flip it, we negate it. All right. So -2 x minus 4 plus -1, so -1. And that would be my equation. All right. So it's a question designed to kind of get you off and moving in the right direction. Nothing too crazy. All right. Number 2, verify whether the following functions are inverses of one another using the composition method. What that means is that I have to compose f and g of x, and the result would be equal to x. All right. If that's true, then f and g are inverses. All right. So if that statement is true, then f and g are inverses. So I'm going to take my f function. I'm going to rewrite it. Open set of parentheses everywhere I have an x. And I'm going to slide into those sets of parentheses the g of x function. All right. Pardon the notation here. The math editor on Brightspace. Technically it works, but sometimes the equation just doesn't show up in the preview. So I didn't want to take a chance. So I just kind of hand typed it. All right. So this is really -1/2. Well, actually, I'll just put g of x over here. And I'll probably need a little bit more wiggle room here. -1/2 x minus 3 in the parentheses. Distribute the 2. So you get -x minus 6 plus 1. Simplify, -x minus 5. All right, that's what we're getting as f of g of x. All right, since f of g of x is not equal to x, f and g are not inverses. All right, so that's a little brief explanation. Show your work, but like the last thing I really want to see is like you do this and write no. Give me a little something. It doesn't have to be like this, but it should be a little bit more than just a yes or no. All right. Number 3, write the equation of the polynomial function shown in the graph below. All right. So to write the equation, we need roots. All right. It looks like I have one here and one. That's a little messy. One here and one here. All right. I'm going to bring it in. All right. So this is the first root, x is equal to 0. So that's this one. And this is 1. This point here is the halfway point between 0 and 1, which makes it a half. All right. So I'm going to say, let me get that out of there. X is equal to 1/2. All right. X is equal to 1/2. Now 0 has a multiplicity of 1 because the curve just kind of cuts right through the point. All right. It doesn't wiggle. All right. If there's any wiggle, then the multiplicity is going to be something bigger than 1. If it behaves like a parabola, like this one does, then that's going to be multiplicity of 2. All right. So actually, let me do this a little bit better. So it goes through quick and to the point. So we say multiplicity of 1. And the other one is multiplicity of 2 because it behaves like a parabola around that x-intercept. All right. So then what I'm going to do is I'm going to write a polynomial. P of x is equal to k times my first factor. All right. X equals 0. The root corresponds to a factor of x minus 0 equal, well, the factor would be on the left-hand side. But if I tried to unsolve this, and you know, when 0 is involved, it's a little weird, but my factor would be x minus 0 equals 0. Right? This is the factor here, the x minus 0, which really just means x. All right. So it's whatever set equal to 0. You know, I mean, you essentially have it here, but if you want to have it in that x minus a form, then this is how you would write it. Either way, it's going to simplify down to x equals 0, or just an x on the left-hand side. Now, for the other one, I got to do a little cross multiplication. So this is 2x is equal to 1. Bring the 1 over. So 2x minus 1 equals 0. And they get cut off there. All right, so the 2x minus 1 is the factor that I'm looking for. All right, so when I say P of x is equal to k times, you know, in the notes, it was k times a bunch of factors. So k times x minus 0 to the first power, then 2x minus 1 to the second power. And again, you don't have to write it like this. You know, you can just write it as just an x. All right, then we pluck a coordinate off of the graph. There will either be an obvious one or it'll be labeled like you see in this example. All right, so let me use the black ink. That point there is my x. The other coordinate would be P of x, or the y value. So -1 is equal to k times 1 minus 0 to the first, 2 times, I'll use a dot, 2 times 1 minus 1 to the second. We're solving for k here. All right, so -1 is equal to k times 1 times another 1. 2 times 1 is 2, minus 1 is 1, squared is 1. All right, so we get k equal to -1. All right, so my P of x is equal to -1 times x minus 0 times 2x minus 1 squared, but I could really kind of clean this up to -x times 2x minus 1, the quantity squared. All right. Yeah, the other thing you could have done, you could live with the fractions. Just we try to avoid having fractional coefficients, but you know, sometimes it's not something that can be avoided. All right. So if I looked at this, just going back here, I could have also said just a simple x minus 1/2 equals 0, with x minus 1/2 being my factor. All right, either way, but I think this is a little cleaner. All right, but it involves the extra algebra step. So, you know, it all depends on what you're willing to, you know, do in terms of the work. All right. So number 4, vertical and horizontal asymptotes. So that's all it's asking. It's not asking for the graph. It's just asking you to state the vertical and horizontal asymptotes. All right. I'll start off with the vertical, the VA. We factor the bottom, and you could also just kind of do it off on the side here. Just clean that schmidgy. All right. The factors of the bottom are x plus 7, x minus 2. All right. I want to take note of that because if there's a common factor between the top and bottom, that common factor would not be a vertical asymptote. All right. Since there is no common factor, well, at least I have the factors of the bottom. So x plus 7, x minus 2 equals 0. X plus 7 is equal to 0. X minus 2 is equal to 0. Solve for the value of x in each case. You get x is equal to -7, or x is equal to 2. All right. Much easier to do the horizontal asymptote. Also something that can be found in your notes, unit 1. Horizontal asymptote, we look at the relationship between the powers. All right. The highest power on the top is the m value. The highest power on the bottom, we call that the n value. Call it whatever you want. I mean, just one letter means one thing, the other means the other. All right. Some people use n and d, numerator, denominator, really however you want to do it. All right. The relationship here is that the m value is less than the n value. So that means that the horizontal asymptote would be y equals 0. All right. If m is less than n, if the highest power on the top is less than the highest power on the bottom, then the horizontal asymptote is y equals 0. If it's greater on the top than on the bottom, there is none. And if they're the same, then it's the ratio of the leading coefficients. All right. Again, all stuff in your notes. Now, when the horizontal asymptote is y equals 0, it's pretty easy to pick up out of a graph. All right. If you're going to do it graphically, though, like you can't just say, oh, it's a miracle. The horizontal asymptote is equal to this. You know, if it's a multiple choice question, that's, or fill in the blank, that's different. But if it's a show all work, then you got to give me something. And that something would be a quick sketch of the graph. All right. So, but yeah, just to do it, I'll grab an f of x here. -3x, close it up, divide x squared plus 5x minus 14. You don't really need the parentheses on the top. You just need it to make the fraction, but it looks nicer without it. All right, pop it in, take a look at the picture, and you could see as you go further and further to the right, I'm just going to do that this way. As you go further and further to the right, the x value is getting larger and larger, but the y value seems to be leveling off. And in particular, it seems to be getting closer and closer to 0. All right, so you could do it that way. But like I said, I would want a quick sketch of the graph. All right. Number 5, little compound interest question. It's compounded monthly. So that's the A equals P times 1 plus R over N to the NT power. All right. The P is the principal balance. It's how much you're starting with. 2,000. The R is the interest rate in decimal form, so 0.021. Compounded monthly, so N is equal to 12. And T is time in years. They're saying over a 10-year period. And of course, just be mindful of rounding. If it's multiple choice, then, you know, the only way I could trip you up is to put the same answer and just round it differently. So just take note of what the rounding instructions here are. So round your answer to the nearest dollar, so it's a whole number value. So we'll keep that in mind. All right. So A equals 2,000. 1 plus 0.021 over 12 raised to the 12 times 10 power. 2001 plus 0.021 over 12 raised to the 12 times 10 power. You could just write 120. And we get about 2467. So $2,467 would be the appropriate rounded value. All right. Number 6, a regular octagon is inscribed in a circle with a radius of 3 meters, which the following is the area of the octagon. All right, this one it's got a little oomph to it. So I'm going to draw a quick sketch. I'm sure it'll be awful. Oh, already off to a rock start. All right, got a circle. No, that's a hexagon. Doofus. Yeah, I can't draw. I'm going to do it by points. Just need something to aim for. All right. That's the best looking octagon I could make. Looks pretty dreadful, but still better than nothing. All right. What I need is the area of the octagon itself. So all of this. So the way we're going to handle it is to use the sector and segment formulas. Area of a sector is 1/2 r squared times theta. The area of a segment, a little bit more complicated, is equal to 1/2 r squared theta minus the sine of theta. All right. Now, a sector, again, just to remind you, because it's been a while, a sector would be this entire area here. All right. All of that would be the sector, including the fringe area. All right. So that's the slice of pizza. The segment itself is this little guy right here. All right. There are 8 of these slices of pizza in a pie, and also in this diagram. All right. So what this is saying is basically how much of the delicious part of pizza, because, you know, people say that their favorite part is the crust. If you say your favorite part is the crust, then you just don't like pizza, you like bread. All right. That's different. All right. The best part of the pizza is the pizza. All right. So, and you know, that's not open for negotiation. That's just the way of it. All right. So what I would need to figure out is all of this area here minus all of this little bit of area here. That'll give me this one triangular area. Multiply that by 8 and I'll have it. All right. So that theta value, theta is going to be 2 pi divided by, well, it's kind of like graphing a trig function. 2 pi over b, b being the frequency, like how many times does the figure occur. All right, the frequency here is 8. Each of these triangular wedges put together make up the circle, and there are 8 of them. All right, so 2 pi divided by 8, but in this context, you'd say number of slices. All right, so pi over 4. All right, they told us that the radius is 3. I won't do any funny business with units or anything like that, so you don't have to worry about like, oh, but they said to the nearest 1/10 of a centimeter squared or something like that. It's going to be consistent. All right, so I get r equals 3. So I want to find the area of the sector, which is 1/2 times 3 squared times theta. So pi over 4. All right. Now you could go decimal, but you got to be fairly precise. If you go decimal, I recommend sticking in fraction form as long as possible. And also, you know, the NumWorks calculator is pretty friendly when it comes to that. Oops. So pi over 4. You know, it doesn't look quite the same, but, you know, when I typed it in, but it is. Okay, so you get 9 pi over 8. You also get the disgusting decimal equivalent, but 9 pi over 8 is the way to go at this point. When you work with the segment formula, it needs to be, your calculator needs to be in radian mode. All right, so again, just a reminder, you go down into settings, angle measure, whichever mode is required for the problem you're working on, in this case, radians, so I'm going to leave it alone. All right, so I need the area of the segment, which is 1/2 r squared times theta minus the sine of theta. All right. And again, NumWorks handles it pretty well. So you could kind of be reasonably confident that it's going to give you something that's conducive to being written down on paper and not like a muddled nightmare. All right. But, you know, you might want to just do it out anyway, you know, like, so I'll do it both ways. So 3 squared is 9, over 2 is 9/2 times pi over 4 minus the sine of pi over 4 is radical 2 over 2. Then distribute the 9/2, so you're going to get 9 pi over 8 minus 9 rad 2 over 4. All right, so again, the sector is all of this. All right, the segment, let me get something that's going to pop out here pretty good, something dark. All right, the segment, I actually got to select it. Hey, where did it go? Oh, there it is. Maybe a little too dark, but live with it. All right, so the segment is this little guy in here. So I'm going to subtract. I really wish I selected colors that I know the name of, like the pinkish one. Maybe that's pink, I can't tell, but it looks different on my iPad screen. And the bluish one, which might be a variation of Hawaiian blue. I'm not really sure, but it does look a little bit like the uniform color for the Detroit Lions. So you never know. So I'm going to subtract those two. So I'm going to take 9 pi over 8, subtract from it 9 pi over 8 minus 9 rad 2 over 4. All right. So this is going to be the area of the triangle. I could distribute this understood -1. So I'm just going to write it this way. So 9 pi over 8 minus 9 pi over 8 plus 9 rad 2 over 4. Something nice happens. The pi terms cancel out, 9 rad 2 over 4. And so if I want the area of the octagon, it's going to be 8 of those triangular areas. So 8 times 9 rad 2 over 4. And so that's going to be 18 rad 2. All right, but they did say to round to the nearest something or other, 10th. So 18 rad 2. You got about 25.5. One of the choices, so that's always a good thing. All right. Just be careful. I'm kind of a jerk sometimes when it comes to multiple choice questions. So one of these choices, I'll just show you. 9 red 2 over 4. Well, actually, maybe I wasn't a jerk this one time. All right, but what I usually do is I put a choice in there of what you would get if you forgot to multiply by 8. All right, so just be careful about that. When in doubt with a question like this, do the work and upload it. Just submit it with another question. That's the way of hedging your bet a little bit. So just keep that in mind. And I think because it was a practice, I didn't really go. I didn't go the devious route with the choices, but typically on the test, at least once, I tend to do that. All right, so number 7, verify the trig identity. So I'm gonna make my impenetrable barrier. I'm going to work the more complicated side, which looks like the left-hand side, right? There's nothing I can really do with that sine of theta, but tangent is sine over cosine. Really nothing I can do with the 1. Secant is 1 over cosine. All right. I'm adding 2 ratios, so I would need a common denominator. So I'm going to take this sine and put it over a 1, take that 1, put it over a 1, and then multiply top and bottom of this one by cosine. And do the same thing down here. All right. Can't assume anything when it comes to a proof or a trig identity verification. So make sure you show the act of multiplying top and bottom by cosine. All right. It's not ideal. I mean, you want to skip the steps, especially if they feel like common sense, but it is a proof, so you have to demonstrate it. It's kind of like when you're reading a textbook and the author of the textbook goes from one step to the next without showing how they got there, and you're like, what'd you do? Like, tell me what you did. That's what I'm looking for here. All right, so cosine theta sine theta over cosine theta plus sine theta over cosine theta, cosine theta over cosine theta plus 1 over cosine theta. I do have a common denominator, so I can start putting it together. So cosine theta sine theta plus sine theta over cosine theta over cosine theta plus 1 over cosine theta. All right. Now I'm going to start, well, first let me move this up a little bit. I'm going to start simplifying. I have a common cosine that could get canceled. And then on the top, I can actually pull out a cosine. Sorry, a sine. I looked away from the screen for a second and I took a chance and it didn't pay off. All right, so I'm going to factor out a sine of theta. And it's going to leave me with cosine theta plus 1. I have the cosine theta plus 1 on the bottom. All right. Now, I just got through saying that you shouldn't skip steps. This is a step that's perfectly acceptable to skip. You showed the cancellation of cosine. So in your mind, you could say, well, my new fraction is this over this. All right. And just kind of look at it that way. All right. So I'm just kind of doing one of these. All right. Nothing wrong with arrows. You can use arrows too. It helps kind of get the point across. All right. We get a cancellation here, and we're left with sine of theta. And the other side is sine of theta. And that's it. I mentioned this, well, at least a month ago when dealing with trig identities. yeah, you want to show all your steps, but every now and then you might run into a wall and say, oh, I don't know how to do this. Like the one thing that you don't want to do is insult my intelligence. Right. So if you're like, okay, I got the first step, I don't know what else to do. Okay, sign equals sign. He'll never notice. Like, don't do that. All right. If you get stuck, just stop where you got stuck. All right. Don't then skip to the, well, but it worked out. Sine of theta is equal to sine of theta. It's kind of a double whammy points wise. You lose the point for not doing it correctly, but then you lose another point for insulting my intelligence. It's not really that. It's that if you jump right to the sine of theta equals sine of theta without justifying it, then that's an incorrect conclusion based off what you've written. Right. So that's why you lose the additional point. Right. So definitely don't do that. The question everybody loves. That was a little bit of sarcasm, but I'm sure there are some people who like it. I actually like this kind of question. It's just if you're not comfortable with the process, it can be pretty frustrating. But I'll just kind of walk you through it again. And also be careful. Like when it says u plus w, I'm looking for u, vector u, and vector w. Right. So when it says u plus w, don't give me u plus v. All right. Now, I mentioned this before the last test. You want to come up with some reasonable facsimile of these vectors on paper. All right. One recommendation I had, and I know you can't see my setup over here, but just hold a piece of paper up to your screen. The backlight is it's gonna make it clear what the vectors are. And as long as you get the general same size and orientation of what's on the screen, then you could work off of that. Right. The alternative would be to use an app, but I know we don't all have that access. Right. So I need u plus w. So I'm going to grab u here. And I'm going to grab w. I have to preserve the orientation and the size. Right. Within reason. So this is my u, this is my w. I'm going to create a little coordinate system here, x, y. I'm going to pin one of them at the origin, doesn't matter which one. Then I'm going to pin the tail on the donkey of the second vector to the tip of the first vector. And then I'm going to connect the origin to that very last point there. And I'm going to label this u plus w. All right. And so that's my first vector sum. When people attempted this on the last test, I noticed that part A wasn't really much of an issue. It was part B that got a little complicated. All right. But if you follow the process, you'll get that too. First thing I would want to take into account that when I have u plus v minus 3w, that's really the same as saying u plus v plus negative 3 times w. All right. So it's ultimately looking at vector w to begin with, and then going off of that. You could also look at it like negative, 3 times negative w. All right, you can go that route too, where you're starting off, and because you got to reproduce the vector anyway, it's really just a simple matter of changing the arrow to go this way instead of what it was originally. All right, but I'm going to start off simple. I'm going to start off with u plus v. All right, so I'm going to get a u. I'm going to get a v. I'm going to get a set of coordinate axes. I'm going to label, I got my u, my v. So I'm going to plot my U, pin it at the origin. I'm going to plot my V, pin it at the tip of U. And the resultant for that will be U plus V. All right. Then I'm going to bring in a W. All right. Now, it's a negative W. So originally it was pointing upwards. It's going to go the opposite direction. And I need 3 of them. Oops, I lost the size relationship there. So I'll have to paste it again. All right. Now, based on where I position this diagram here, that's going to go off the page. So I'm going to slide this over. And, you know, the pencil paper analog to this would be, you know, do a rough draft first and then do your final copy. Right. Otherwise, you could be looking at this and saying, well, I started my graph over here and it's off the page, and you get the Scotch tape out. It's a nightmare. All right. So that's part B. Now I'm going to take the tail of this scalar multiple and pin it to the tip of U plus V. So this vector here, the whole shabiggity bangity boomity boom, is negative 3W. Let me get a fresh new color in here. All right, so the resultant going from the origin between U plus V and negative 3W will be this blue vector here, which I'm going to call U plus V minus 3W. All right, so that's probably the most involved one, only because, you know, you saw it. I mean, it's like I started my graph a little too far to the left or a little too far to the right, and you pay a price for that, but it's not insalvageable because, or unsalvageable, because you could just do it again, get another piece of paper out and do it again. All right, I learned my lesson. I went too far to the right. Let me go a little bit more to the left then, you know, something like that. Now, the last question could be really any of these possibilities. All right, so I'll take you through, well, I guess I could do them all. A polynomial function graph, you need all the ingredients, you know, like when we talked about it, it was the X, Y intercepts, the behavior, whether it's behavior around the intercepts or behavior in the end sense, so the end behavior of the function, all those different possibilities. But let me just throw in an example here. Let's say you have, and again, you're going to make one of these graphs, not all of them. All right, so just keep that in mind. So let's say I have P of X is equal to 2, I'm going to go 2x, x minus 1, x plus 1 squared. All right. Now, for symmetry, you know, because this is a final exam and not like the actual unit test, you know, you can cut some corners, just don't go too crazy with it. But for symmetry, I'm fine with you just popping it into the calculator and seeing whether or not it's symmetric. All right. So not designed, when I design a final exam, I don't design it to be a test of mastery of every little topic throughout the course. It's more like general strokes. Like, what are the most important topics, and do you have a solid understanding of it? All right, so that's really what we're after here. So if I plot the graph I don't see any symmetry. Now, I do see a bunch of things like x-intercepts, a y-intercept. I see some turning points. I have a general sense of the shape of the graph, so that's good news. All right, so my x-intercepts I would get by setting each factor equal to 0. All right, first one and second one are easy. The last one, I'm going to take the square root of both sides. So x plus 1 is equal to 0, so x is equal to -1. All right, because this was a power of 2, I know it's multiplicity of 2, and each of these are multiplicity of 1. All right, and that's because those factors were raised to the first power implicitly, but still. All right, the y-intercept, you get the y-intercept by running a 0 through the entire function. So p of 0 turns out it's equal to 0. But I mentioned that you're forgiven if you don't remember every single thing I said from throughout the course. But if an x-intercept is equal to 0, then that must also be the y-intercept. Right? Symmetry. So no symmetry. So you just make that statement. All right. End behavior. So when we talked about this way back when, I said you sort of have to imagine that you're distributing the whole thing out, right? And what would you get? Right. So if you were to distribute this out, you'd get a 2x times an x times an x squared as your first term. So that would be 2x to the 4th power. All right. So this is the first term of the expansion. All right, because you do a little FOIL, first, outer, inner, last, double distribute. That last binomial, that binomial squared, would be the first term of it would be x squared. Right. So what we get out of this is that it behaves like a quartic. Right. So behaves like a 4th degree polynomial. It's kind of a weird way of phrasing it. I can't off the top of my head think of a better way to phrase it. I mean, it behaves like a 4th degree polynomial because it is a 4th degree polynomial. Right. But what I mean by this is that it's got a W shape or an M shape. All right. But even that is like, you can see in the picture, So then I create the graph. -1, 0, and 1 are my important values. All right. I know it's going to come down, grab this point. It's going to turn around. I can sort of cheat off of this a little bit and grab those. Why does it keep jumping? I'm like accidentally hitting the up and down arrow at the same time, or up and left arrow. About half a unit up. So if I'm calling this 1 here, then I'm going to have a point. Oh, sorry, a little too high. Point about right here, about right there. And let me go down and grab this one here. And that's a little bit less than 2 units, 1 unit down. So call this -2 here. So this is -1, -2. So somewhere in this neighborhood here, I'd have another point, goes through 1. So we're going up, grabbing this point, going down, grabbing this point, and there we are. All right. So it's kind of, I don't know. I don't want to say pointless because, you can see I plotted like 4 points. It's more like it's using the calculator as a supplement, but you getting experience with the general shape of different polynomials to set you up for success in calculus. Rational function graph. So and I'll give you r of x is equal to negative 2x over x squared minus 9. And if you remember during the unit, I said we need important coordinates. I'm sorry, important boundaries. So that would be the horizontal asymptote and the vertical asymptote. All right, the horizontal asymptote, just like the one before, the power on the top is less than the power on the bottom. So that would be y equals 0. Horizontal asymptote, x squared minus 9 equals 0. So x squared is equal to 9, meaning x is equal to plus or minus 3. All right, so we have our asymptotes. We want our x and y intercepts. All right, if you set the function equal to 0, this is actually one of those where I can just write it because it's pretty straightforward. If I set this equal to 0, I'm going to get negative 2x equals 0, which means x has to be equal to 0. And the y-intercept, and again, like I said before, if the x-intercept is 0, then so is the y-intercept. So creating my graph, I'm going to have asymptotes 1, 2, 3. 1, 2, 3. Oh, little spacing issues there. I don't know if it's going to get any better. I know it's going to go through the origin, and it's going to approach the line y equals 0, but I don't know if it's going to be like a this, or this, and so on. So you could use test coordinates, or you could just pop it into the calculator. Negative 2x divided by x squared minus 9. I just need a general shape. So plot graph. All right, so it's going to look like this. It's going to grab the origin, and then it's going to look something like this. All right, and so that would be my rational function. Nothing too crazy. I mean, I would say that this is probably one of the simpler graphs to produce. There's a lot less going on. You find those 4 ingredients: horizontal, vertical asymptotes, x and y intercepts. Sometimes there's a hole, so you got to be careful about that, but it's fairly manageable. Then I said a sine or a cosine graph. I'll do a sine function. All right, so little graph paper goes a long way. I mean, you got the weekend before the exam. If you don't have any graph paper and you're doing it pencil paper, you may want to print out some. I'm not saying go buy a book of graph paper, right? But you can go and Google graph paper and it'll come up and you just print it out, or like I mentioned earlier in the course, or actually in preparation for the last test, you could just use a graph that we haven't used. So there's a graph grid in the notes that you printed out way back when. We didn't create a graph, so use that. All right. You could also do it freehand if you're really neat. Right. That's a little trickier. So we'll do the sine function. So let's say it's y is equal to 2 sine 2x minus pi plus 1. Right. So the a value is 2, the b value also 2, c value is negative pi, and the d value is 1. A for amplitude. The b value is the frequency, but I need that to find the period. 2 pi over b, 2 pi over 2, which is just a pi. All right. The phase shift is, equals. Phase shift is negative C over B. So negative pi over 2. And D is the vertical translation. All right, so it's a vertical shift. But if you remember, I know it's been a while, but I abbreviate that VT is equal to 1. All right. So now what I want to do is sketch out this graph. Like I said, maybe a little piece of graph paper. All right. So I'm going to draw a horizontal line, a vertical line. I didn't indicate what the domain should be. So I'll stipulate that. I'll say negative 2 pi to 2 pi. All right. Just be mindful. It could be really anything. All right. But I'll give you a domain if I give you the trig function. All right. So it takes pi units to go one full cycle of the sine function. That's what the period tells me. So I'm going to let's see how many boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm going to go 6 units for pi. It's a little weird. I'll just go 4. So here's pi. Here's 2 pi. Here's negative pi. Negative 2 pi. And I keep saying you might remember, but I'm just going to stop saying that because maybe you don't. We make a rough draft first using dashed curves, and then we put our final product as a solid curve. All right. So with an amplitude of 2, so I'm going to let one box equal 1 unit. So this is 2. Here's negative 2. I'm going to produce an entire sine function between 0 and pi. All right. Everything important in a sine function happens in quarter unit increments. So it's going to start at the origin, hop up to the maximum at the quarter wave point, midline at the midpoint, 3/4 wave point, it's at the minimum, and then back to the midline. So that's what an ordinary sine function with an amplitude of 2 and a period of 2, a period of pi would look like. All right. So I can continue that trend throughout the entire domain. All right. So that's what a full negative 2 pi to 2 pi of a sine function with an amplitude of 2 and a period of pi would look like. But now I have to account for my phase shift, right? Pi over 2 is half of pi. So this is 2 boxes left and 1 unit up. So every coordinate that I plotted is going to go 2 to the left and 1 up. So this point over here, start using my highlighter or my pointer. So this point here is going to go 2 to the left and 1 up. So it's going to go right here. This point, 2 left, 1 up. So right here, 2 left, 1 up. Two left, 1 up. We'll do a few more. You'll see the trend. 2 left, 1 up. 2 left, 1 up. Sounds like I'm saying the number 2 left, 1 up. Up where? Who knows? All right, so this is a little bit of the curve. If I follow the trend, that gets me back over here. Oops, a little wonky there. All right, so just keep following that trend. Until you run out of domain. All right, so the red one is the final. You don't really have to label it. If you're doing it using dashed versus solid is always the one, is the actual graph, right? So anything that's solid, if you do it all in the same color and didn't have any labels on it, the one that is solid is the one that I would look at as your final answer. But if you really want to drive the point home, throw a highlighter on it. Oops, I mean, throw a highlighter on it, but do it well, as opposed to what I just did. So you could do that, or you could say this one. Yeah, however you want to indicate your final answer. All right, but again, if it's solid, I assume that that's what you're saying the final answer is. All right. Next up is, a polar graph. Okay. So let me snag a polar graph from somewhere. Let's see, I have one in my scrap notebook here. There I do. All right, so let's say we have, this was C, so I'm going to go D. Let's say you have R is equal to 1 minus, I'm going to say 1 minus the sine of 2 theta. I'm going to say 1 minus the sine of theta. Because it's really more about the process than any kind of like overly complicated example. All right, so make a table of values. The table of values should consist, or must really consist, of only nice numbers for sine. All right, so theta, 0 is nice for everything for the most part. Pi over 6, pi over 2, 5 pi over 6, pi, 7 pi over 6, 3 pi over 2, 11 pi over 6, and 2 pi. And if I need to sort of backfill it with more, more points, I can do that too. All right. So yeah, this is kind of like a basic version of a polar graph. So it doesn't include the over 12s. So this is pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, pi. But you could get you could just use a ready-made one. I'm doing this because this is the first one I found, but like a ready-made polar graph is fine. I need 5 pi over 4, but I've gone down this rabbit hole, so and we have 0, 2 pi. All right, so when I plug in a 0 for sine, I get a 0. So that's the pole. Maybe I don't need to make that as thick. Just kind of get it. Oh, I want a red. Pi over 6, sine of pi over 6 is 1/2. So 1 minus 1/2 is 1/2. So I'm saying half a unit in the direction of pi over 6. It's going to be really, really in there. Pi over 2 is the value of 1. So 1 minus 1 is equal to 0. And apologies, it's at this moment that I realized that that 0 wasn't the final answer for 0. It's 1 minus 0, which is 1. All right. Now, fortunately, this one gives me a point at the pole, so I don't have to worry about erasing it, but sorry. So one step in the direction of 0 is the point that I'm missing. So that's this one here. 5 pi over 6. Result is 1/2. So 1 minus a half is a half. So that's half a step in the direction of pi over 6. If it's this small, scaled this small, then you may want to let like 2 boxes equal 1 unit, or even 4 boxes equal 1 unit. But I have the ability to zoom, so it's not a deal breaker in this case. Sine of pi is equal to 0, so 1 minus 0 is 1. So there's one step in the direction of pi. That would put me right here. 7 pi over 6 is negative 1/2. So 1 minus negative 1/2, that's 3/2 or 1.5. So 1.5 steps in the direction of 7 pi over 6. 3 pi over 2, sine of 3 pi over 2 is negative 1. So 1 minus negative 1 is equal to 2. 2 steps in the direction of 3 pi over 2. 11 pi over 6 is negative 1/2. So 1 minus negative 1/2, 3/2. So 3/2, so 1.5 steps in the direction of 11 pi over 6 puts you right there. And again, I know it's like teensy tiny. And 2 pi is going to get me back where I started. So 1 minus 0 equals 1. There's no new coordinate there. All right. So I could draw my cardioid. Well, actually, this one's a limacon, but it looks a lot like a cardioid. All right. So that's what the graph would look like. And again, for scale, maybe you want to, let it be equal to 2 rings is equal to 1 unit. So each ring could be half a unit or a quarter of a unit, whatever you think. And the last type of graph is a conic section. We focused on 2 of them. One is the hyperbola and the other is the ellipse. So I'll just do the ellipse here. All right, so let's say we have x minus 1 squared over 4 plus y squared over 9 is equal to 1, always equal to 1 in standard form. Actually, I guess I can't do it there. I'm out of room. I'll just try to keep some of this up on the screen. All right, so for the ellipse, we need the a value, which is the square root of the denominator associated with the x term. So a is equal to 2. We need the b value, which is 3. We also need the center. That's 1, 0. We need the vertices. Now, vertices are all 4 of them. So when I say vertices, it also accounts for co-vertices. All right, so we need those as well. You could start the sketch. It is an ellipse, so it's not that bad. But you also have to account for the coordinates. So I'm going to kind of do both simultaneously. I started framing it kind of like a trig graph there for a sec, but it's okay. So 1, 0 is right here. I'm going left and right 2 units. I'm going up and down 3 units. All right. So my vertices, the longer axis is the major axis. So my vertices are 1, 3 and 1, negative 3. My co-vertices, negative 2, 0. I'm sorry, negative 1, 0. And 3, 0. Connect with a smooth curve. best you can. Even before it auto-corrected, it would have been fine, you know, like in terms of credit. All right, but then we need the foci, the coordinates of the foci. All right, we get that by solving for the using the Pythagorean theorem. All right, so we have, this is my half of the major axis, and here's my minor axis, or at least half of it. This distance is 2, this distance is 3, so we're looking for this. Oh, sorry, I pinned it the wrong place. Let me just bring it in. That's, the foci are going to be somewhere along this. I have no idea where, so we'll revisit that in a minute. But this distance is 2. This distance here is the same as this distance here. All right, so this length is the same as that length. All right, so we call that 3. We know it's a right triangle, so I'm going to let X mark the spot. The foci, X squared plus 2 squared is equal to 3 squared. So X squared is equal to 3 squared minus 2 squared. So X is going to be equal to the square root of 3 squared minus 2 squared. All right. Now, the reason I'm doing it this way is just to kind of emphasize the point where if you have your A and B values, whichever one is bigger, square it and subtract from it whichever one is smaller. And you'll have a nice little shortcut for figuring out the location of the foci. All right. So 9 minus 4 is 5. So rad 5. That's 2 and change. All right. But in terms of the coordinates, that's going to be, it's going up and down from center. So leave the X value of the center alone. 0 plus or minus rad 5. Or you could just say plus or minus rad 5 because 0 is immaterial. All right. So that puts my foci, you know, I took a stab at it and I was a little off. You know, it's probably something more like this. You know, it's a little bit further out in space, but, you know, it's not the end of the world. I'm just going to plot a point here, call that F1, and a point over here, which we'll call F2. And again, this is another one of those instances where you may consider scaling your graph. All right. And so the last thing would be the hyperbola, or the last type of graph would be a hyperbola. All right. And again, it could be any of these. It's not going to be all of them. It's not even going to be more than one of them. It's going to be, I'm going to ask you to do one graph where you make it out, you know, the whole shebang, but I'm not going to tell you in advance which one it is. Okay. So you got to be prepared for all. All right. So I'm actually going to use the same equation, except I'm going to put a minus sign in between. All right. So it should streamline things a little bit. So E, this is E, right? Hyperbola. So X minus 1 squared over 4 minus Y squared over 9 is equal to 1, right? So my A and B values, my center, they're all going to be the same. The vertices and co-vertices are all going to be the same, right? And that's one of the reasons why, you know, just kind of get things moving here. All of that stuff is going to be the same. All right. So I'm going to plot 1, 0. I'm going to go left and right 2 units. I'm going to go up and down 3 units. But this time I'm going to make an asymptote rectangle. All right. I'm going to just do this real quick. Divided by 4 minus y squared over 9 equals 1. And then plot the graph. I'm going to go auto. Actually, that's not working. So let me do axis. I'm going to go -5 to 5. And I'll do the same for y. All right. So I'm bringing this up because on the last unit test, I noticed some people for the hyperbola question, they created an ellipse, and that's, it can happen, but if you put it into your calculator first and you look at the picture and say, wow, that is absolutely not an ellipse, then at least you're kind of steering yourself in the right direction. All right. So diagonals, again, they're going to be dashed. And this one opens outward because it is a hyperbola equation that begins with an x. All right, the x term is the one that's positive. I'm going to just kind of move this over here. And because of that, it opens left, right. If it were the x term that was negative, then it would open up, down. All right, so we're looking at something like this. Oops, ran off. And like this. And then we just have to plot the foci, or find and plot the foci. You remember I gave you the shortcut formula. Distance from center to focus is equal to the square root of the bigger denominator plus the smaller one, although it doesn't really matter because addition is commutative. All right. And the foci are always on the transverse axis. So this is going to be a left-right measure. So my coordinates would be 1 plus radical 13, 0, and 1 minus radical 13, 0. Radical 13 is a little bit more than 3.5. So from center, I'm going to go right 1, 2, 3, and change. Call that F1, 1, 2, 3, and change. We call that F2. And that would be my hyperbola graph. All right, so that's pretty much everything. I mean, well, anything that you would need to be concerned with for the final has been addressed. So hopefully that was helpful. All right, so at this point, I'm going to stop the recording.